We are going to look at biological treatment today, which is another unit operation. It's more or less the heart of a wastewater treatment process. Would involve using microbes to treat the wastewater. Please bear in mind, we don't use microbes to treat drinking water, although it can be involved microbes in the treatment of drinking water. But here we talk about the wastewater treatment. I've seen in the past years, students get confused when they apply the biological treatment to treat drinking water. That is not the case. Here we talk about wastewater, so bear that in mind. Now, going back briefly about the treatment process, just a quick reminder. So it involves different stages, and typically a wastewater, particularly domestic wastewater, would have typically the same process unit operations almost anywhere in the world. Yeah, there are some variations, but generally you will find these primary treatment, secondary, and tertiary treatment in certain cases. But if you look at the treatment process, we have the bar screens, we talked about that, grit removal, the first settling tanks to remove suspended solids and any solids left in the wastewater. And after those settling tanks, the wastewater is generally free of solids. However, there will be some left solids. You can't guarantee that these units will 100% remove the solids, but the majority of the solids have been already removed at these points. And there will be some left solids, generally suspended solids, okay? So that little fraction of suspended solids plus what is dissolved as organic matter into the wastewater. And that dissolved matter, it's not going to be removed by any of these unit operations. So you need another unit operation to remove that organic matter. Perhaps if you are a chemical engineer or possibly environmental engineer, you would say, I'll use a chemical reaction to remove those organics in wastewater. You could do that, and from a technology point of view, there is no reason why you can't use, for example, strong oxidants or strong reactants to react with the dissolved organics in the wastewater, and you remove them. But that will cost a lot. That would be an expensive operation that is not feasible from a practical point of view. First of all, you are going to deal with an extremely large volumes of materials where the interest for you, it's only small amounts of molecules that are problematic. And when I say that, is we talk here about milligrams per liter level of materials that are problematic that you need to remove. So applying other technologies can be possible, but it's going to be expensive and it's not feasible. One way you could use is to use natural kind of inspired treatments, and that based on microbes that are available in nature, and we know them, they eat, between brackets, that organic matter that is dissolved. So you send those army, if you want, of microbes to the wastewater, and they will find all organic molecules that they love to eat, and they will eat them and they will treat the wastewater. I'm putting things in a very simple way, so hopefully you understand the concept of why we need biological treatment. There is also economics around that need to be respected and would be the main driver for using the biological treatment. So the biological treatment, in simple terms, they're the secondary treatment, as we classify them in the wastewater context. They involve using microbiological species to remove the dissolved fraction of the organic matter that is problematic in the wastewater. And also they could remove as well part of the suspended particles that are still into the wastewater. That's the heart of it. That's the main purpose of the biological treatment. What type of systems we can use? There are different biological reactors. The most famous one is the activated sludge although it is a new technology-ish. When I say new, it's say around the 60s, started to get into the wastewater. But before the activated sludge process, which we'll talk about in more details in a minute, we have other types which have been used for long times, yeah? And that would involve, for example, trickling filters. And basically trickling filters is a filter where you have stones, and those stones, you let the bacteria to grow on their surfaces. And when the water passes through those biofilms, we call them, of the bacteria that are attached to the surface, then what's happened is you have the treatment. And these rocks or stones, they have gaps between them, and those gaps eventually will bring the air and oxygenate that environment. So you have oxygen that is naturally coming to the environment, you have the wastewater percolating through those rocks, and you have the rocks containing the microbes that you need for the treatment. That's the trickling filter concept. And also you could have ponds and lagoons, which is a practiced system as well from antiquity possibly, where you have the wastewater just settling in a lagoon, and you will have microbes there to do the treatment, as well as you have sedimentation in those lagoons. So that's the secondary treatment, and that's the purpose what we are going to look at today. These processes obviously produce solids, and that solids is called sludge, and those sludge, they need to be treated in specific treatment systems before disposal. Okay. I almost told you the whole story to some extent of the biological treatment, but also to get few aspects and language that is used in biological wastewater, which possibly you are familiar with, things like aerobic, anaerobic, and facultative types of microorganisms or bacteria. The aerobic ones, they require oxygen for their metabolism or growth. Anaerobic, they can grow in the absence of oxygen from air. However, they can get their oxygen from species such as sulfates, for example, it's SO4, so there is plenty of oxygen there, or from nitrate or carbonates, yeah? And when you have microorganisms operating under such conditions, when you don't have oxygen from air, but you have these sources of oxygen, sulfate, nitrate, carbonate, we call anoxic conditions, okay? Facultative types of microorganisms, they are clever ones where they can grow and proliferate in the absence or in the presence of oxygen. So they can stand basically, if you have oxygen, they don't mind. And if they don't have oxygen in the environment, also they don't mind. So they can grow under various conditions of oxygen. But from a treatment perspective in the wastewater, we generally use the aerobic type of microorganisms. So you require oxygen to be delivered to the system for these bacteria to grow. Okay, and also we use the anaerobic type of microorganisms to also treat the wastewater. So generally, these are the two types of microorganisms that can be used into the wastewater. I talked about earlier about the attached growth processes, and that's where you have things like rocks or plastic or wood, where you have the microorganisms growing on their surface. And here an example of a plastic material that is used to attach the microorganism. I'm not sure if you can see my screen, but you can see there is a slight layer you can see attached to the plastic material, and that layer is the microorganisms. Obviously, this is like new technology as compared to simply the rocks. What do you think the difference between this type of technology, where you use these plastic materials, in comparison to rocks, for example? As an engineer, what would straight away come to your mind why we need to use these plastic materials? Very good. Yeah, surface area. You can see clearly for the same volume, you will have a much higher surface area when you use this type of packing as if you have rocks, for example. If you have a rock, you could imagine it's all that volume is occupied and the only surface available is the outside surface. But with this one, you provide a much larger surface area. And these processes are surface processes that you have interest to increase the surface area. So that's the attached growth type of process. You need a support material, and on that support material you will form biofilms of the microorganisms where they grow and they proliferate when they have contact, where they are in contact with the wastewater, and they use the materials that are in the wastewater to grow. That's the attached growth. The other type of processes which is widely used is the suspended growth processes. And the suspended growth type is you have those microorganisms. Generally, the microorganisms, they won't form just one microorganism on its own. Generally, they flock together to form some sort of solids, blocks if you want, and those solids, they can vary in size, maybe a few millimeters, maybe micrometers, etc. But what is it is you have those particles of microorganisms, they could float into the water. So if you suspend them, if you use a mechanism to suspend those microorganisms into the water, that will give you even higher surface area and contact between the water and the microorganisms. Yeah. So if you think about a particle that has a diameter d, the specific surface area for that particle, as you may know, it's 6 divided by the diameter. So if your diameter goes down, the surface area of contact will goes up. Okay. So in our case, you have those particles, you suspend them in the wastewater, and they will give you the treatment of the wastewater. And the most famous type of processes that works on the principle of suspended growth is the activated sludge, which we'll look at it in a minute. But you have an example of activated sludge in here, where you have a tank, and at the bottom of that tank you have a supply of air. The supply of air will have 2 roles. First of all, to provide the oxygen needed for the bacteria to grow. You need oxygen, and also that air will mix the content of the reactor and therefore will suspend those microorganisms to occupy the total volume of that reactor rather than settle at the bottom of the reactor. So that's quite important. And you can see the air here on the top of an activated sludge process. Okay. The other way, by the way, to suspend the microorganisms, you could have your reactor like that, and if you have a high-speed impeller, well, I wouldn't say high speed, but it's at the right speed, yeah. But it's not slow as well. So it has an optimized speed. That speed, and you keep agitating the top layer of the liquid, what's going to happen? You're going to suspend the whole volume of the liquid as well. So that's another technology which is widely used in the wastewater industry. Briefly, we're not going to go in deep into the chemistry of the microbial growth, but simply you could look at it as a chemical reaction where it involves the use of organic matter, for example, represented here by sugar, and you require oxygen and certain nutrients, for example, ammonia or a source of nitrogen, etc. And in the presence of microorganisms, all that organic matter in the form of, for example, a glucose molecule there, will form new cells. That means new microorganisms. Obviously, that equation is not a true representation of a cell, but it gives you an indication of the content of a new cell, which involves carbon, hydrogen, nitrogen, oxygen, etc. Okay, so that's the biological reaction. It can be seen as a chemical reaction involving all these components in there. One key variable that is of interest to us in the wastewater context is the biomass yield. And that biomass yield, Y, it represents how much biomass you produce in mass term, for example, how many grams of biomass you produce per mass of substrate. Now here it gets a bit tricky, by the way, because two things. First of all, you can't measure the biomass as such, so you need some sort of a surrogate way to measure the biomass, one. Second, when we talk about substrate, we know that the composition of the wastewater is extremely complex, and therefore we can't measure the composition of the wastewater for every single substance in that wastewater. So we need to use another surrogate to measure the content of the organic matter or substrates into the wastewater. And we talked about this before, and that surrogate involves using the BOD or COD. Yeah. So in summary, these are important terms from the wastewater context, and please put them in your heads, is that when we talk about biomass, you're not going to count how many, for example, microorganisms or how many bacteria you have in the wastewater, but what you need to do is to find a surrogate way to measure the content of biomass, and I'll show you in a minute how you do that. But in all cases, it is measured as VSS, volatile suspended solids. And if you recall these various types of solids, the diagram we had before, hopefully you'll see what is it, but I'll show you in a minute. So the biomass, you have the VSS to represent the biomass content. And for the substrate, we use BOD and COD as we defined them before. Going back to the VSS, if you remember, the various types of solids in wastewater, we need to do this type of experiments. We take sample, we can evaporate it, we could use the Imhoff cone, or we could filter it. So if you filter your sample, and then you evaporate what you obtain on the top of the filter, that gives you the total suspended solids. And if you place that filter, which is made of glass fiber, so it can withstand a muffle oven at high temperature, 400 degrees C, then you obtain two fractions, the volatile solids, suspended solids, and the fixed suspended solids. So that volatile suspended solids, it's a representation of the amount of bacteria that you have into the wastewater. And as you can see, that's more or less a surrogate way to measure the amount of bacteria or microorganisms you have in the wastewater. And this is very important in terms of the significance of the value of VSS. So it's quite important when you characterize wastewater. VSS represents the amount of microorganisms to some extent in the wastewater, and it's been used to develop the equations for biological treatment that we use in the design processes. Okay, so in summary, to make things simpler for you, VSS would represent you the mass or the amount of microorganisms in the wastewater, and BOD and COD represents the substrate that these microorganisms use to grow. So this table shows typical values for the Y, which is the mass of microorganisms divided by the mass of substrate. That means if you have a gram of COD, for example, and if you apply microorganisms or biological process to treat that wastewater, then you expect to produce for every gram of COD 0.4 grams of microorganisms as measured by VSS. That's the meaning of it. Okay. If you use, for example, anoxic condition, then you produce less. So you produce 0.3 gram of VSS per gram of COD. And if you have anaerobic conditions, even less of VSS you produce per gram of COD. So that table gives you an idea, in a way, how much of the microorganisms you produce. And in fairness, that has a lot of implications in the design, and that why will be quite important in the design of biological treatment. Briefly, you may be familiar with this bacterial growth curve, and just to remind you about this curve, how the bacteria grow in a real test. If you take initially a suspension of bacteria and you put enough food there for it to grow and enough nutrients, and you count the number of bacteria you have initially in the sample, then you see that number of bacteria, for example, it started from there and 0. And over time, you keep measuring the amount of bacteria in that sample. What you see is that the number of bacteria initially will keep constant. It doesn't change. It keeps almost the same value as you started with, and that is called the lag phase. And after a certain time, you can see the number of bacteria start to grow exponentially, and that's the exponential phase, where you have the food to the microorganisms is reasonably high, about 1. That means you have sufficient food for the microorganisms to grow, and then they will grow exponentially, up to a certain point where the amount of food, or the ratio between the food and the microorganisms, obviously gets down, because the microorganisms consumed the food and kept producing more of it, more of microorganisms. Yeah. So at a certain point, you will reach some sort of equilibrium between the amount of food available and the amount of microorganisms available, and that reaches a plateau, stationary phase. And at that stationary phase, we have the food to microorganisms ratio is around 0.4. Okay, and after some time, if you continue doing that test for longer time, what's happened, the microorganisms will eat most of the food, all of it, and nothing left of substrates. To understand what I meant by food, think about like you have sugar, for example, in water. So that microorganisms are using it. So at a certain point, there will be no sugar for the microorganisms to use and grow. And then what's happened, the microorganisms turn around and found another microorganism, and basically they start to fight each other and kill each other. So, and what's happened after that, when the food is finished, that number of bacteria will start to go down. Okay, and that's the decline death phase of those microorganisms, because the amount of food is not sustained anymore. Okay, to be honest with you, if you think about it, that's how humans would interact as well. Yeah, so the concept more or less is the same there. And this is the decay phase. So what we are interested in here is how to use these information for our design. And as you can see, we need to think about this exponential phase, the increase, the growth of the microorganisms, but also you need to think about the ratio between food and microorganisms, and also you need to think about the decay rate. So all these are important variables or parameters that you need to consider in the design, and hopefully we'll see that in the kinetic equations in a minute. Okay, so put in mind the food to microorganisms ratio is important. The rates by which the microorganisms grow is also important, and the rate by which the microorganisms would decay is also important. Okay, generally you aim to operate your reactor of biological treatment within this phase there, where you have the food to microorganisms ratio, say around that 0.4. In addition to the food, which is the organic matter that is available in the wastewater, you also need to have other conditions available for the microorganisms to grow nicely without being being dead, basically. And for that, things like, for example, temperature will be important, light, pH is extremely important. And also you need to provide as well nutrients for the bacteria to grow. If you give a solution of glucose only to microorganisms, you won't expect the microorganisms to grow. So you need to have other nutrients such as nitrogen and phosphate into solution. From an engineering point of view and a design point of view, if you are working in a wastewater plant, your aim is to have that ratio between carbon, nitrogen, and phosphorus should be in this range. For every 100 portion of carbon, you will need to have 10 portions of nitrogen and 1 portion of phosphate at least, up to 100 for 5 and 1. I would retract the use of at least because there is an optimum. If it's too much nitrogen phosphorus, that can be also not good for the reactor to operate properly. So there is this optimum ratio between carbon as measured by BOD5, total nitrogen, and the total phosphorus should be within these limits, okay? And this is key. There are a load of perhaps people, they operate the wastewater biological treatment and they don't have knowledge of all these concepts of like the ratio between carbon, nitrogen, phosphorus, and their systems are failing and possibly they don't know what's going on. So if you have that case, then you need to measure how much BOD5 you have, how much TN you have, and how much phosphorus, and then you will see if those ratios fall within those ranges or not. If they are outside that range, perhaps you need to do something, whether be it you add more nitrogen or you add more phosphorus or you find a way to reduce phosphorus and so on. So that's quite important. And this leads me to think, if you are dealing with wastewater, particularly industrial wastewater, where the problems generally arise, then you can't guarantee in an industrial wastewater to have these ratios all the time correct. And if it is the case, then you need to intervene and, as I said, add, for example, nitrogen source or phosphorus, or maybe speak to your domestic wastewater treatment process and get some of their wastewater to make that balance of BOD5, TN, and P. In the domestic wastewater, generally the wastewater would have those ratios well established. Okay, briefly about the kinetics of biological growth, how the cells would grow in a reactor. We can make reference here to our concepts we know in the chemical reaction type. You know, first order reaction, second order, etc. But generally, we use first order reactions to describe the growth of bacteria into a biological reactor. And that reaction is described by this rate equation, where the rate of growth of bacteria would be equal a constant mu, although that is not constant, and we'll see in more details what that mu represents. But if you make reference to the first order reaction kinetics, that you have the rate equal K times the concentration of the substance of interest. So in our case here, we have more or less similar equation where the rate of growth of bacteria equals specific growth rate mu times the concentration of bacteria X, okay? So one thing to put in your minds now, to make it simpler when you see these equations, capital X represents the concentration of microorganisms that we are considering into the reactor. And that capital X can be, for example, VSS. Okay, you remember that VSS I talked about? So that is the X. X represents the VSS. So X represents the concentration of microorganisms. Mu is the specific growth rate. And Rg, it is the change of X over time, which represents the rate of growth. If mu is constant, then what you have first order reaction, you integrate it, and you would obtain the change of the concentration of microorganisms as function of time, where xt equal x0 exponential mu t. Now, how does x change? Mu change, the specific growth rate. How does it change? The specific growth rate is a function of the concentration of the substrate. So mu can be considered constant under certain conditions, particularly when you have the substrate is at high concentration. Then mu is constant, and therefore the rate of growth of the bacteria follows an exponential type rate. And if you go back to this curve, this is the part where we have the exponential phase, where the amount of substrate is very high. So that S is constant. That means mu is constant, therefore you have an exponential growth. In the general context, that mu, the specific growth, is equal to a maximum specific growth, mu max, times S divided by Ks plus S. And this is the famous Monod equation, which describes the limiting substrate or nutrients into biological reactor. It's very important equation when you're dealing with kinetics in the biological term. So please put it in your heads. Mu, which represents the specific growth rate, it is equal mu max, that's the maximum specific growth rate, times S over Ks plus S. Ks is a constant, half rate constant or saturation coefficient, but it is constant. And S represents the concentration of the substrate. How do you measure S? What variables you use to measure S? S represents the substrate, represents the food, if you want, the microorganisms need to eat, which are the organic molecules in water. How we measure them? Very good, very good. Yes, yes, excellent. So S represents the concentration of the substrates that are in the wastewater, which we measure through the BOD or COD. Yeah, very good. So combining all these reactions, all these equations together, you obtain a rate equation for the growth of bacteria that is given by that equation. Just simply replace mu by its equation, and you obtain Rg equal mu max xs over Ks plus S. In the same manner, we can look at the rate of substrate utilization. That means how the BOD or COD, that's the substrate, when I'm making reference to substrate, how does that change over time, yeah? So that concentration of substrate changes over time and is represented by the rate of substrate utilization. And we know, if you remember, we defined the relationship between the growth of bacteria and the substrate utilization using the yield coefficient Y. So that relationship between the two, the rate of growth and the rate of substrate utilization, is defined by this relationship where it involves the yield coefficient Y. And since we defined already the rate of growth for bacteria, therefore we have the rate of substrate utilization, which will be minus 1 over Y of the rate of growth. And you obtain that equation for substrate utilization. Why we have the minus sign? Because from a reaction point of view, what you are doing, you are utilizing the substrate. That means the concentration of the substrate is reducing over time. So the rate of substrate utilization is obviously negative because you are consuming the substrate. However, when you consume that substrate, what's happened is you produce the bacteria. That means the rate of growth of bacteria is positive because the number, the mass of bacteria, or VSS, which represents the bacteria, is going up. And therefore its growth is positive. So one of them is consumed, one of them is produced, and that's why you have the minus sign. In addition to the growth of bacteria, you have also the decay. If you remember when I said when you don't have sufficient food for the bacteria, then what's happened? you will have a decay phase. So there will be decay of the microorganisms. And that decay is represented by, again, another first order with a minus sign because you are decaying the bacteria. And the rate constant for that decay is Kd. So that also needs to be taken into account. And overall, the rate of growth of bacteria will be that only what entity of the growth due to the substrate, which we defined earlier, mu max xs divided by ks plus s, and you need to take from that the decay rate. So that's the general rate of growth of the microorganisms, would involve as well that Kd. And you have everything more or less to describe the growth of bacteria. The other point to mention that those rates are function of temperature. So temperature plays an important role in the growth of bacteria. And generally, the rate of growth, or the rate RT in general, at temperature T will be the rate at the reference temperature, which is generally 20 degrees C, times theta power T minus 20. You remember this equation when we talked about it for BOD. So it's the same sort of equation. And this theta is found in tables, like here. For example, when you are dealing with activated sludge, typically the value of theta 1.04, aerated lagoons 1.08, and trickling filters 1.035. All these theta values are obtained from experiments. These are typical rate growth of microorganisms, different types of microorganisms into wastewater. And as you can see, these growths are not the same. So depending on the microorganisms, you have different type of growth. These some photos of different microorganisms that you found in wastewater. So you have all sorts of types of microorganisms there. Touch on biodegradability, which I did before. Biodegradability, it measures the how biodegradable the wastewater of interest. And that simply would involve measuring the BOD to the COD ratio. If that BOD over COD ratio is within certain values, then the wastewater is biodegradable. If it's low, then the wastewater is not biodegradable. And here I give you some examples of BOD over COD for a landfill leachate, which is problematic wastewater in the environment. And that ratio, BOD5 over COD, is classified based on the age of that landfill leachate. If it's just a new landfill leachate, its BOD5 to COD is 0.7. That means it's biodegradable. You could use biological treatment to treat it. Mature 0.5, aged landfill leachate 0.3 until it gets old, where that ratio is 0.1, which means the landfill leachate is not biodegradable, and you need to have the more it gets older, the more it gets difficult to biodegrade. And then you need to use different other processes to make that landfill leachate biodegradable. I talked about this before when I introduced the problem, but just to emphasize the point about the attached growth process. So you have a media, for example, a rock or plastic media, where you have the biofilm, and then you have the wastewater phase there, and you have air. So from a mass transfer point of view, this is a very, very interesting problem. What involves? It involves a flow of wastewater like that, and you have the transfer of oxygen from the surrounding air to that wastewater, and then from the wastewater, the oxygen will be transferred to the biofilm. Okay. In addition to the transfer of oxygen from the wastewater film, you have also the transfer of organics from the wastewater layer or film that forms on the top of the biofilm to the biofilm, where the biological reactions will take place at that point. And then you form end products, for example, CO2, or ammonia or whatever products you form, these products, they need to be transferred in the opposite direction from the biofilm to the wastewater. And some of it, if it's a gas, will be transferred from the wastewater to the air. So this is really an excellent example of chemical engineering in action, basically. Yeah, where you show all these mass transfer processes. And if you guys have interest in this area, particularly from a research point of view, these phenomena need more work to understand what's happening, in fact, into those reactors. So there's a lot of research still need to be done around that area. Trickling filter, maybe mention one number here. It's the depth of the media we use is generally between 1 to 2.5 meters. You don't want too deep packing media. It will cause all sorts of issues. If it's too deep, maybe it will be difficult to get the air to pass through, etc. But that's the design of it, of a trickling filter. This is how it looks like. You may see these type of filters, for example, from Google Images or satellites. These are trickling filters. When you see these disc rotating, that pipe with holes there rotating, that is distributing the water throughout the filter. This is how they look like in real life. That's the pipe distributing the water on the top of the filter. These design numbers that you need to consider if you are designing a trickling filter. Some of the problems with the filters, you may have growth of vegetation like that. You may have ponding, where the water will be more or less form ponds on the top of the filter because the flow it's not good enough. Maybe it's blocked the filter, and also you may have flies, which can be a problem for these filters. I mentioned earlier about the plastic, so it's good to have plastics because they provide much larger surface area for the process to happen. This gives you a comparison between the two. For a filter, you may have 150 meters squared plus per meter cubed versus 60 roughly to 120 at max meter squared per meter cubed. So if you use plastics, you almost double the surface area. Other types of biofilm reactors, for example, the rotating disc biofilm reactor. So you have a disc like that, and you have a contactor where the water comes in, and that disc keeps rotating to oxygenate the biofilm that forms on the disc and bring it into contact with the water. So that's another technology. Obviously, this is if you have a small flow of water that you need to deal with. For large volumes of water, that's not practical. For example, the food industry, they use these type of reactors to treat their wastewater. This rotating biological reactors images, some of them you may cover them. You may cover the biological reactors to avoid odor, for example, and flies, etc. The aerobic type of suspended growth processes that would involve the activated sludge mainly, but also aerated lagoons, sequencing batch reactors, anaerobic digest and membrane bioreactors are these new types of reactors that are gaining interest. They are more or less the same as an activated sludge process, but the only difference between the two is the way how you make the separation between the sludge you form, the solids you form, which represent the microorganisms and bacteria that are formed in the reactor. In the traditional activated sludge, they use simple sedimentation. In the membrane bioreactor, use membranes to do that separation. To describe the chemical engineering processes that happen in these reactors, you simply use your mass balances, which involve the input minus output, plus minus either formation or decay. It is equal the accumulation. So that's the general mass balance equation that I'm sure most of you are familiar with. You apply it to these reactors and you obtain the equations that you need to describe the reactors. This is the case when we have a complete mixed reactor with the flow coming in and flow coming out. There is no recycle, but we'll see the case when we have recycle. And no need, I think, to go through all the details on how to obtain these equations, but from the mass balance, you will be able to develop these equations. I made emphasis on the amount of the food to microorganisms ratio. That's very important variables in the design of the reactor. Sludge age is important, how long the sludge would reside in the reactor, and also the oxygen transfer rate. So these are important factors to consider for the design. Briefly, the activated sludge, what does it involve? So you have a biological reactor, or it's called aeration tank, where you have an influent flow of the wastewater coming into the biological reactor. Usually that influent comes after or from primary settling. So you have the primary settling, and after it, you have the biological reactor. In here, in the biological reactor, you have a suspension of microorganisms where the influent get into contact with those suspension of microorganisms. That suspension of microorganisms is done by supply of air, whether be it using diffusers at the bottom of the reactor or using a high mixing by shear force that is due to a turbine at the top of the reactor. And then once you do that biological reactor there, you pass the flow, which involves water and solids of the microorganisms, into what we call a secondary clarifier. And that's simply a solid liquid separator. And then you obtain in that secondary clarifier the liquid effluent at the top, and you obtain in the bottom of that secondary clarifier the solids part. And when I say solids part, don't think about it like rocks, really, of solids. No, but it's a mixture of solid materials into water. And generally, the water is much higher proportion than the solids, but it's highly concentrated mixture of solids. And those solids, what we can do, these are made of microorganisms that are still live, that they are still happy to eat more more food, more organic matter in the wastewater. So instead of wasting them all of that microorganisms, what we do, we waste only a fraction of it, and another fraction is recycled back into the aeration tank. Because these microorganisms, they are still live. They are happy to keep eating, between brackets, the food that is coming into the wastewater. So, and that's the trick really about the activated sludge. And if you want, that's the patent, how they got around this system, is to recycle a fraction of that material back to the aeration tank. And that is called the returned activated sludge. And this is the waste activated sludge or surplus activated sludge. The recycle has to be properly designed in order to provide the sufficient biomass in the reactor, and that to involve to get that ratio, food to microorganisms ratio, correct. This is the activated sludge process, how it looks like. These are the bottom of it, what involves the gas diffusers to diffuse air into the reactor. You could have surface aeration, I talked about, when you have a motor and an impeller there agitating the surface of the reactor, and that would oxygenate the volume of the water. These are gas diffusers. This is another picture of the final settling tank, the secondary. After you form those sludge, they will settle in this type of tank. And in the next session, I'll go briefly about the various equations we need to use in order to design the activated sludge system. Bye now.